Hi, I'm Faustina, and I'm here to explain the context of our latest work on automatic differentiation and to convince you to read it. There are a few approaches to differentiating programs, so why choose automatic differentiation? One well-known approach to differentiation is numerical differentiation. This allows us to obtain approximate numerical derivatives via, for instance, divided difference methods, but runs into accuracy problems. The most obvious way to avoid approximation errors is to avoid approximation entirely. Symbolic differentiation does this by working on closed-form mathematical expressions and applying the familiar calculus rules for differentiation. However, symbolic differentiation can be impractical due to computational redundancy, as illustrated by the terms highlighted in red. The language of mathematical expressions isn't as expressive as a programming language. In maths, we can't take advantage of, for instance, let bindings. Gradient-based optimization algorithms need to compute partial derivatives of a function with respect to many inputs, and both numerical and symbolic differentiation are slow at this. Numerical differentiation needs to be run separately for each input, and symbolic differentiation unnecessarily reevaluates repeating expressions. Automatic differentiation addresses these weaknesses. It is a source-to-source transformation on programs, generating new programs which can compute analytical derivatives of the original program. AD is expressive and exact, and furthermore can be made fast. Thanks to these advantages, it has become an indispensable tool in contemporary artificial intelligence, most notably in machine learning via frameworks like TensorFlow, PyTorch, or Julia. Consider this toy program F. AD will translate f into a new program df, which can be used to calculate the derivative of the real number output with respect to the real number input for any set of inputs. The type of df depends on the AD method we use. We only consider derivatives of real number outputs with respect to real number inputs. For instance, we don't look at the derivatives of the Boolean output or take any derivatives with respect to the Boolean input. There are two types of AD translation: forward mode and reverse mode. Both forward and reverse mode produce derivative calculating programs which are parameterized over a point in the input space. A forward mode translation tells us the direction in which the output of a function changes, given a direction of change in the input. Reverse mode works the other way around, telling us the direction of change in the input, given a direction of change in the output. While forward mode is simpler, reverse mode is better suited to optimization problems with many inputs and few outputs, such as machine learning. For instance, if you're using gradient descent to optimize a model with 1 million parameters, you can ask reverse mode what direction in the parameter space would reduce the loss the quickest. A single pass of reverse mode is sufficient to calculate all the required partial derivatives, while forward mode would require 1 million passes to do the same job. Our main contribution is to give a simple and efficient implementation of reverse mode AD, which works on a fully higher order language with first-class anonymous functions and has a runtime and memory consumption linear in the runtime of the original program. In addition to a formal description of the translation, we also describe an implementation of this algorithm and prove that it actually calculates derivatives by means of a logical relations argument. Automatic differentiation has a rich literature and many complex and impressive implementations, but it is hard to find an approach to AD that does all these properties at once. Our algorithm has the same features as many deployed systems, recording and replaying a kind of execution trace. However, our principled step-by-step development makes it easier to understand, easier to prove correct, and hopefully easier to use as a basis for exploring design variations, as we indeed do in our paper. By reading our paper, you can enjoy a remarkably straightforward formalization of forward mode and reverse mode AD, understand how reverse mode works in relation to a standard explanation of forward mode, and see a monadic AD translation that does reverse mode on a higher order language and appears to be new, as other work uses side effects to achieve efficiency. While no single aspect of our paper is new, the combination is, and we hope our account, which uses only elementary concepts, can serve as a clear explanation of AD to any POPL attendee.